Hello everyone, my name is Motaz Ayiad. Today I will be presenting the progress on my topic enhancement to SCADA EMS for hybrid AC-DC networks. Mainly I will be talking about my recent publication state estimation for hybrid VSC-based HVDC AC transmission networks. Let's start with the one slide revision. The state estimator is a toolbox available on the SCADA level. It aims to provide better system state values like voltage and phase angles on the AC side and voltage on the DC side. There are many state estimation algorithms available nowadays, including extended Kalman filter, least absolute value, and weighted least square algorithm, which is used in this work. The unified hybrid state estimation, which is based on the weighted least square algorithm, is basically a modification over the normal or traditional AC state estimation using PWLS. The modification included integrating with the DC measurements and two terms related to the converter. The first term is power coupling, and the second term is voltage coupling. The power coupling. The power coupling is a constraint that finds a relationship between the power injected to the converter and the power injected out of the converter and the power converter losses itself inside the converter. The power converter losses does not include the transformer filter reactor losses. Instead, the TFR losses are included and considered in the AC side estimation. The main contribution of the power coupling is improving the measurement estimation in general. On the other hand, the voltage coupling factor, or the Mfactor, or as it's called in some lectures, the modulation factor, is basically finding a relationship between the voltage of the converter at the DC side and the voltage at the AC side of the converter. The relationship basically can be reconstructed as constraint or kept as a measurement sent by the converter to the SCADA side. The main contribution of the voltage coupling is improving the system state estimations. In addition, further modifications has been made to the Jacobian matrix. These modifications include additional components and partial derivative to the power coupling and the voltage coupling. Let's start with the traditional components, AC and DC components. On the AC components, we can see that the partial derivative of the measurement functions of the AC components, or the AC measurements, to the voltage and the phase angles, while on the DC side, they are only partial derivative to the voltage. But when we go to the power coupling component, we can see that on the DC side, it's much easier to calculate, but on the AC side, it's more complex. The reason will be just because of the existence of the current element. For example, here we can see the partial derivative of the power coupling constraint to the voltage and the phase angle of the AC side. To the left, we can see to the voltage, and to the right, we can see to the phase. The same thing has been done to the voltage coupling, but the voltage coupling doesn't have any phase element or current element. Therefore, both the DC side derivative and the AC side derivative, they are easy to find, as we can see also here for the AC side. The algorithm has been tested in several test cases, including the Cigre B4 DC, which includes 6 AC systems, 2 DC systems, 8 AC generators offshore and onshore, 11 converters, and 5 demand nodes. 109 measurement has been used in this test case. All has been corrected with a 3% error, while the Mfactors only has been corrected with 1% error. The weights of these measurements are shown in the table below. The noise measurement were generated in the following manner. It's a true measurement plus the error, and the error is generated by the Gaussian noise. The Gaussian noise is a mean equal to the true measurement and the standard deviation calculated can be seen in this equation. The proof of this equation can be found in the appendix of the below reference. After running several simulations, we can find the following results. First of all, that the unified approach was able to minimize the error, or the main average error, compared to the other two approaches on the measurements level, AC and DC. Well, when you look at the system state values, we can see that the decentralized approach in the middle has shown more error than the other two approaches. But when we look on the AC systems, mainly AC system 1 and AC system 2, because they have the most number of buses, we can find that the unified approach was able to better estimate the phase angle compared to the other two approaches. When we look at the PV coupling, or the power and voltage coupling, we can see that on the left side, that the constraint error is almost 10 to minus 5, while the Mfactor is almost to 10 minus 3. Despite the great accuracy that is provided by the unified approach, we can see that also there is one downside of the unified approach, which is the time performance. The decentralized is almost 62% faster than the unified approach, and also it requires less memory allocation compared to the unified approach. For further details and more depth about mathematical background can be found in this paper, the state estimation for hybrid DSC-based HVDC AC transmission networks. But as usual, the HDCU does never stop working. So if it has break or not, we still have to keep working. And after I finished the previous work on the previous paper, I've already started with a new topic, which is in the same field, but more focusing about the time cycle. And what I mean by time cycle is basically trying to find the minimum time to complete a state estimation cycle from the time of sensing the measurements up to the time of processing these measurements and showing up the state estimation results. As in this case, we are using the Cigre B4. We have virtually installed 43 RTUs and 10 data concentrators. We have 2 stages of data collecting, starting from the RTUs to the data concentrators, and then from data concentrators to the server side. The communication medias and protocols are still to be defined. That's it for now. Thank you for listening. I hope you enjoyed the presentation. Stay safe, and I'm looking forward for your questions and to hear further details or suggestions. Take care.